Hello everyone, I am Setareh from Queen's University, Kingston, Canada. I present our paper Self-supervised Human Activity Recognition by Learning to Predict Cross-Dimensional Motion. This is a joint work with Michael Rainbow and Etemad. Human activity recognition is a popular field of research because of its wide applications in different areas such as health, personalization of user experience, and sports. Due to the pervasiveness of smartphones and wearable devices, massive amounts of wearable data have been collected, which as a result has created new research opportunities for activity recognition studies. Although fully supervised techniques have shown robust performance in activity recognition area, there are some challenges that they might face. First, these approaches are highly impacted by the amount of training data and require large sets of labeled data. As we mentioned, collecting this large activity data is feasible. However, annotating them is a problem since it is expensive and time-consuming. Secondly, such approaches learn very task-specific representations, which may not be easily used for other similar tasks. To leverage this unlabeled data, self-supervised or semi-supervised approaches can be useful. So, in this work, we propose our self-supervised solution for human activity recognition based on cross-dimensional motion prediction. Using this approach as the pretext of the self-supervised method results in learning generalized and informative motion representations. Our approach consists of two phases. First, the pretext, which is our cross-dimensional motion prediction, and second, the downstream, which is the human activity recognition task. We create fixed size windows from the acceleration data containing three axes, x, y, and z. Then we break each window into two segments by assuming the last time steps of axis z as the output segment and the remaining values of axis z along with the values in axes x and y as the input segment. We implement a network containing convolution and fully connected layers to learn to predict the output segment from the input one. In other words, our model leverages the past and present motion in x and y dimensions, as well as past values of the z-axis to predict values in the z dimension. As a result, the model learns to extract strong motion representations from the acceleration data. After we're done with the pre-training, we freeze the convolution part of the network and pass it to the next phase, in which the frozen network followed by a MLP classifier are used for the human activity recognition task. We evaluate the robustness of the proposed model with comparing the performance of the model with other self-supervised methods such as multitask and mask reconstruction-based approaches for human activity recognition on three activity datasets. The proposed method outperforms all other approaches. Moreover, we compare the performance of our self-supervised model to a fully supervised one with the same architecture when different amounts of label data are used. It can be observed that when only small amounts of label data, like only 1%, are available, the self-supervised model clearly outperforms the fully supervised one. It shows that the proposed method can learn to extract effective representations even with small amounts of label data. So, to put it all together, we propose cross-dimensional motion prediction as a novel deep self-supervised solution for learning representations from unlabeled accelerometer data. We demonstrate that our method outperforms existing self-supervised methods in human activity recognition for UCI HAR, MotionSense, and HAPT datasets. We also show that in cases where really small amounts of labeled data are available, our self-supervised model clearly outperforms the fully supervised approaches that are using the same architecture. Thank you, everyone.